Thanks a lot for dialing in. I appreciate it. This is our third weekly session of DynamoDB office hours. We'll be doing this ongoing for some period of time here, I guess, until at least you guys tell me that you're not interested anymore. But that doesn't seem to be the case. So that's actually really good. We are here today. We're going to talk a little bit about. Actually, I've had a lot of questions about the tool that I'm using. There is a session that's up online, but the video quality isn't so great. So we decided to go ahead and kind of do that again, redo that session today on office hours with a little bit different schema. But it's around purchase orders. We're talking about purchase order processing system. And we're going to be really showcasing the DynamoDB, the NoSQL Workbench for DynamoDB, which is the tool that I've been using in the last couple of weeks to kind of show you these models. So we're going to dive a little bit into the functionality there. It's really an exciting tool. It does a lot more than just modeling. So we'll talk a little bit about that today. Anyway, so let's with that, let's kind of get started. We'll talk again, like we always do. We'll talk a little bit about the use case that we're trying to solve here, and again, this is about purchase orders and purchase order processing, and we're really not talking about an online ordering system, although it might be, and those online ordering systems scale significantly. But generally speaking, if we were to look at purchase order processing at a wide scale, we'd really be looking at that SMB sector. 95% of the applications out there, what do they scale to? What's the velocity of those workloads? What are these systems designed to support? This again is the schema that we're going to kind of be looking at today. These types of schemas define the entity models that we're going to be working with more or less. In this case, we can see we have kind of this purchase order entity. We have associates that work with purchase orders. They apply notes to those purchase orders that kind of define the relationship that they have. There's really got more or less a many-to-many relationship between the associates and the purchase orders because of these notes. Again, notes have activity codes and whatnot. These types of tables, you probably notice after a while, we tend to denormalize a lot of these types of code tables and things like this because in most systems these things don't change very much, and I get a lot of this. But what happens when they do? And back in the day, I guess you'd say, when relational databases were developed, the cost of processing large data sets was tremendous, and the idea of having to update denormalized data was very painful. And so this is where a lot of the kind of conceptual belief of it's hard to do that, but the reality is today processing power is enormous and available on demand, especially in cloud. Being able to table scan a DynamoDB table is really trivial. I mean, I can increase the capacity to what I need to get things done quickly. So let's not worry so much about the denormalization and updating those items when they need to be updated, because it's really not that painful of a process especially for things like this, right? When we have these activity codes, they're relatively infrequently changed, infrequently updated, if ever. I don't really want to hinge the development of my system on my ability to update data that's more or less immutable, and that's really the point here. So that's when we get into the modeling, you'll see more or less this process. Again, we have vendors. Vendors, another entity in the system. We have inventory items that are related to purchase orders through the details, which really describe the items that are in the purchase order, and so on and so forth, right? The inventory categories, the cabinets that the items are stored in. It's a relatively complex schema here we're going to be looking at, but when we get down to the modeling, it's really not terribly complex. And when we look at the velocity of the data and the size of the data, I think the best place to go look at would be that retail sector. This is where you're going to see the highest velocity, right? Consulting sector is probably not doing thousands of transactions a second. So what are these retailers really doing? And it turns out, honestly, actually not as much as you might think on an individual, retail location. They're the velocity of these things is reasonably low. So when you look at the average transactions in XMB retail, values in velocity, where was the transaction size? How many transactions, right? Average retailers process about 482 transactions per store each month. These obviously aren't like grocery outlets. These are more places where you would see, purchase order type activity. You could even process, though, if you think about grocery stores and whatnot, they're not even processing thousands at a retail location. A large, HEB here in Texas, or a large, supermarket in other locations, they're not processing thousands of orders per second either. So we're looking at relatively low velocity transactions, and really it's more about the kind of aggregations and lookups and the workflows that exist around these POs, right? So let's talk about some of those things and what we're going to actually be looking for today when we get into modeling this data. And so this is kind of, I just selected a dozen access patterns that relatively innocuous, get PO by ID, probably going to get all these entities by ID, right? Get me a vendor by ID, get me associates by ID. Those are kind of given the access patterns, basic patterns. But then we're going to want to get all the POs for maybe an inventory item within a given date range, the POs for a given associate that they've worked on by date range, maybe by activity code, by vendor. Get me all the incomplete PO items by date range. Get POs by inventory category. And we'll kind of get into this when we model, but you'll see there's a variety of patterns we're going to try and solve for here to kind of give you an idea of what the flexibility of the table can, what kind of flexible access patterns that we can support with a NoSQL database, right? It doesn't, we don't necessarily have to have really complex data structures to do this, and we'll get into how that works. One of the things I want to talk about as well, which I don't know if it gets enough airtime, is really the DynamoDB free tier and the AWS free tier in general. When you start thinking about applications and deploying applications, there's going to be a certain size of application that actually with DynamoDB is fairly large, which can operate in that free tier. I mean, we're talking about 25 gigabytes of data. We've got 25 WCUs, 25 read capacity units, and this is a WCU that's transactions per second. So, and with the burst bucket, we could talk a little bit about that in future sessions, but the ability to scale this system is fairly significant because we have, within every DynamoDB table, there's a 5-minute burst bucket that builds up of unused capacity, which is available for you to tap on demand at any given point. So even workloads that are relatively sparse but hit hard can run in the free tier on DynamoDB. So this makes a very flexible system to support applications like this, right? So may have some spurious activity which can exceed, those 25 WCUs or 25 RCUs, but I'm not going to be running at a sustained rate that is at that peak. Then maybe if even a free tier application can support that. So when we start designing applications, it's really about cost, and if you can run an application in that free tier on DynamoDB, that's a real bonus to be able to at least launch a service, get it out there, and see what sticks, right? So anyways, let's get into the meat of the session today. We're going to talk about the NoSQL Workbench for DynamoDB, and we're going to model that system, that purchase order tracking system that we just mentioned. And so this is the DynamoDB, or the NoSQL Workbench for DynamoDB. It's really a neat tool, and it was developed by the service team to satisfy the needs of our specialist SAs out in the field, working with customers. The customers also came to us with questions about, they needed tools to help support modeling their data. We had a lot of best practices that we were pushing out there that came out of efforts that teams like our DynamoDB Black Belt team, which I ran for several years, which was focused on migrating our internal services, and those data models, those patterns, design patterns, and best practices were great, but there was no tool to help customers model things. And we would go up there and we would whiteboard these tables, and they go, "That's great. Well, how do I build that in a way that I can share with my developers and put into my design documentation?" And so this is what this tool is built to do. So the first thing we want to do when we work with the tool is create a data model. In this case, it's going to be our purchase order model. You can give it some metadata or not. In this case, I won't. And so what we're really doing now is kind of building a virtual picture of the table. We're going to create partitions on the table. We're going to add attributes to the table. And the first thing we're going to do is add a table and define it. And as all my tables in DynamoDB, some of you will know, some of you who are just joining us might not, I like to use generic attribute names. Oops, that's a table name. And this would be just data. I like to use a lot of generic names for my tables because I don't like to, I like to put a lot of types of objects on the table, right? So if we put a lot of types of objects on the table, then I can't really use strongly typed attributes because not all those object types will have the same attributes. So we're going to use generic attribute names. In this case, PK, partition key, SK, sort key. We're going to add some other attributes later, but the first thing we're going to do is define the partition types. And those really map to the entity types of our model. So if I go take a look at our model, at this point, let's go ahead and save this, add this table definition, and we can go to visualize the model. We're going to add some sample data here. Let's go ahead and edit our data, add some rows. First thing we're going to have is a purchase order partition. And I'm also doing this one a little differently than I've done the other ones. I have no, I posted that schema last week. I haven't looked at it since. This is the first time I'm looking at it. I kind of defined those access patterns this morning. And it's just really more like that kind of flow that I'm going to be going through with the customer the first time I talk to them about their workload. What is it that we're trying to do? What are the access patterns we're trying to support? And here's the type of model that we're going to build. So in this case, we have a purchase order. Purchase order is going to have some item inside of that purchase order partition, because that's really what this is. It's a purchase order partition. We're going to add some items into this partition. And that's one of the things I like to also do, which I didn't do. And let's do that now. I like to add a type attribute to all my objects so that I can tell when I'm looking at the model, what type of object it is. And so let's add that attribute so that now when I create my data, I can update each one of my data types. So this is a purchase order. And inside of that purchase order partition, we're going to have a couple things. If I go take a look at our model, let's take a quick pop back to the model, and we can see that purchase orders have purchase order details, they have notes, and we're going to add objects into this purchase order partition to represent the rows of these tables. That's really kind of what we're doing, is we're going to add all these rows to the model just like we would across all these tables in an existing relational database, but we're going to actually collapse these rows onto the same table, and we're going to do them by following these relationships that are defined in our model here. And so if I have a one-to-many relationship between the purchase order and the purchase order details, I'm going to create a purchase order partition. I'm going to insert the item that represents the purchase order, and that's all of these fields right here. And then I'm going to add purchase order details, one for each purchase order detail. I'm going to add another item to that partition, and that's what we're kind of doing here to kind of visualize that model in the workbench. So let's take a look back at our workbench. And where am I? Too many windows. All right, we should have the workbench up. All right, so we're back in the visualizer here. Oops, I don't want to do that. That's probably making it way too big for you, or way too small for you. All right, so here we go. We've got the purchase order partition defined. We're going to add some other things to that purchase order partition. So inside of purchase order partition number N, purchase order ID, we are also going to have, what do we say? We have some details, which are really items or inventory items. So we'll call that an inventory item, and that might be inventory ID. And this is a PO detail, is that right? Let's pop over to the model real quick here. Yeah, it's a purchase order detail. So it really is an inventory item, though, indirectly. If I look at the model here, let's bring that back up. If I look at the actual model I'm modeling, a purchase order detail maps to an inventory item. And so if I actually identify the purchase order detail associated to the purchase order by the inventory item, then I'm assuming that there's only going to be one inventory ID, I won't have multiple purchase order details with the same inventory item. And that's, I'm going to go ahead and make that assumption in the model here that it's not explicit in this model, but if I talk to the customer, I'd say, well, is it possible for a customer to come in and issue a purchase order with multiple details for the same inventory item? And they would say, oh, yes. or no. Let's assume that they say no. So again, this is, you get the idea. What we're going to end up doing with our data model in NoSQL is we're tuning it to the customer's implementation. Or, I'm not trying to be generic here. I'm being very specific, and we're always going to be specific that way. So this would be actually a PO detail, because it's not really an inventory item, but I can represent it by inventory item ID because, and maybe I want to do an index on inventory ID to get all the purchase orders for a given inventory item, right? That's actually one of our access patterns, right? So that's the next item we're going to add is going to be our note for a, let's say for a associate ID. And on this, I'm going to have some sort of note ID because associates might have multiple notes within a given purchase order, and they might take different actions. If we look back at the model, I'm probably not showing you the workbench right now. Let's go ahead and transition that again. I added one more item in here. This is a note, and this is going to be coming from an associate. But I can't really put the associate ID here because when I look at the model, I've got a relationship that is a many-to-many between associates and purchase orders, and there's many activities and priority codes that could be assigned to notes, so it kind of is implicit in the model here that an associate may enter multiple notes on a purchase order for different reasons. So in this particular case, then, what I need to do is actually have an actual note ID and not associate ID, to guarantee uniqueness of this item within the partition, within the purchase order partition, right? Because again, the combination of the partition key and sort key are what guarantee uniqueness of the item on the table. That is the primary key. All right, so let's go ahead and create a few more partitions here. What do we have? We have an associate partition, and he's going to have a record that describes him. He might not have anything else in his partition because we're probably going to get all the notes, all the POs, all that through the relationships between the associate and these items, right? These note items. Did somebody have a question? Can you zoom in on the model a bit? Yes. I can try and view, zoom out. Oops, that's not the way to go. Zoom in, zoom in. Is that better? One more? Okay, so let's go ahead and add some other partitions here. If I go back to the model, we're going to look at and say, okay, I've got the purchase order, and I've got the associate partition. What else do we have? We have vendors, we have inventory items. Let's go ahead and get our vendor partition in there. And he's going to have his own record there, and he's a vendor item. And again, this vendor is probably not going to have a lot of items inside of his partition because he's going to be associated to the purchase orders he's making through an index on the extended attributes, right? We're going to show that later, is how to get all the purchase orders for a vendor on the extended attributes. Oh, you want to zoom in on the ER diagram? Okay. Let's see if I can do that. I'll zoom back out a little bit on the model, and we'll go ahead and zoom in. Is that better? Hopefully. What we're really interested in is not so much the details of the actual attributes. I'm not even going to put all these attributes into this modeler. What we're really interested in is the relationship between the entities, right? And that's what I'm modeling. In the end, when we go ahead and define the items that we're going to stick in the table and all that, they're going to include all these extended attributes. But when I build models in Workbench, I don't typically include all the extended attributes. What I'm going to do is I'm going to define the keys, and I'm going to define the partitions, and then I'm going to include the extended attributes I need because those are the ones that will be on my indexes, right? So let's get there in a second. We'll get to indexes, but let's continue on with our partition types. We're going to look at What else do we need to add? We have a vendor partition now. I need to add inventory items. I need to add cabinets. The rest of these tables, generally speaking, I don't know if we're really going to get down into the details of modeling by bay and by shelf type and all this kind of stuff. I don't have access patterns defined there. A lot of these things like inventory category, inventory subcategory, those are going to get denormalized into the inventory items in our model. I don't necessarily need to, and if I need to get all the inventory items by a given category, what I'll end up doing is defining a GSI on the inventory item attribute that is indicating what category it's in. But the information around, what, this particular item might be denormalized into each individual inventory row. We'll see. I mean, it depends on how we look the data up. But suffice to say that a lot of these end tables here might end up as a denormalized part of the items that they're related to. And again, because, how often do inventory categories change? I've worked for one of the largest retailers in the world, and I've worked on services like this, and I can tell you not often. We might add new inventory categories, but existing inventory categories typically don't go away. They do. Certain things get restructured, things like this, but those types of operations are not common. This data is relatively immutable, and it's easily denormalized into your model. Generally speaking, but this is the types of questions we're going to have with customers when we talk to them about the nature of their data, right? What's the frequency of change here, and what's the need to maintain, top-level data versus denormalized data. Okay, so let's look at what else we need. We need inventory items. Let's transition back to our workbench. We're going to look at adding a few more partition types. So this is our inventory. An inventory item describes information around the inventory. Let's call it inventory. And is there anything else? Yeah, we'll probably have a cabinet. So a cabinet. And that's a cabinet. So that's generally speaking the top level entities in our model. Purchase orders, associates, vendors, inventory, cabinets. And so let's go ahead and save that. We can take a look at what that looks like now from an aggregate perspective. And what we have is a purchase order partition. We have a various partition types. And if I go, like I said, all my basic access patterns of select purchase order by ID. When I select purchase order by ID, what do I get? I get the item that describes the purchase order. In essence, I'm really getting this relationship. I'm getting the relationship across the purchase order, the notes and the details, or the inventory items that are in the purchase order. I might not get information like the vendor's information unless I choose to denormalize some of that information into the purchase order's A record, right? Now it's up to you. You can decide when I look up the purchase order, is it important for me to have vendor information as well? If that's true, then don't just create, every time I create a purchase order, a vendor creates a purchase order, I might go ahead and denormalize some of this vendor data, which exists in this table, like maybe the vendor's contact information. Maybe I don't need all of it, but I want some of it. I would go ahead and denormalize that information into this because, most of this vendor information, again, is not, highly mutable. It doesn't change all the time. It only changes, and sometimes you don't necessarily want some of the data that changes. I actually want to capture on the PO and say this was the data when this PO was issued, right? If that's the case, then more or less when a purchase order is made, some of this data becomes immutable, and that should be denormalized onto the purchase order, right? So in essence, the first access pattern says get me the purchase order by ID is satisfied off the table. It gets me the entire history, all of the inventory items. It gives me all of the notes. It gives me the top level item that describes the purchase order. I might choose to insert another metadata item in here that describes the vendor, or add that vendor metadata to this, A record for the purchase order. But that's more or less defines the purchase order partition. The rest of these partitions are single item partitions. They're, the associate that describes, what the associate's, item looks like. They're the vendor that describes the vendor's, metadata. It's the actual inventory item, describes the inventory metadata. It's the actual cabinet item, describes the cabinet metadata. And there might be, some sort of a, again, denormalized data, right? Do I really need to have an extra partition that describes a shelf duty type, and then, or can I just denormalize the actual shelf duty metadata into each cabinet item? I can probably do that. Cabinets don't necessarily change their shelf weight, descriptions and their physical descriptions. They typically, this data is more or less immutable when the cabinet's defined, at least in most of our fulfillment centers, and so on and so forth, right? These are this is data that doesn't change frequently. It's easily denormalized. I don't necessarily need to create a complex hierarchy of items that can be described. I can create single items that roll these things up into them, more or less. And they're not even search dimensions, right? I'm not necessarily saying, and maybe they are, depending on the access pattern. Maybe a customer says, hey, sometimes I need to go get all the cabinets that have a shelf rating of 150 pounds or more, right? Things like that. This is really gets into more detail that we would want to disclose before I actually start modeling. How would I create these items? How would I map this data? At a high level, I would look to these tables to say this is candidates for denormalization, right? These are candidates for denormalization. But again, maybe not, depending on the specific patterns. In the patterns that I have described, not so much. All right, so those are the top level entities: purchase orders, associates, vendors, inventory, cabinets. We have our access patterns that we have defined. Let's go take a quick look at those. Make sure that we have all these things defined in our access patterns, right? Get PO by ID, get vendor by ID, get associate by ID. We have some, I didn't have get inventory item by ID, but we have multiple, get inventory item patterns, get inventory items by cabinet, get low inventory items, so on and so forth. Looks like, generally speaking, that our base partitions have been mapped. So let's take a look at these patterns that we have resolved. PO by ID. Then we need to get POs by inventory item by date range. Okay, so that's the first index that we're going to create. We want to get all the POs for a given inventory item in a given date range. And so the first thing we're going to do there is go back to our workbench and build that structure into our model. Let's go do that. And to do that, we're going to have to edit our table. We're going to have to add a few more attributes to the table so that we can create an index. And so one of our attributes is going to be, and again, I like to use generic names for indexed attributes because we're going to have multiple items on our indexes just like we have multiple items on the table, and those items aren't always necessarily indexed on the exact same attributes. So we use generic names so that the values that we stuff in there can be dependent on the type of the object. And then when we query the index, the filter conditions and the key conditions that we use will dictate which types of objects come back. Okay, so in this case, we're going to say we have PK1, SK1, and then we're going to add a global secondary index on those attributes. This will be GSI1 with the partition key PK1, sort key SK1, and we're going to add and save that. So now we have the data table with one GSI. That GSI is called GSI1, and we can go ahead and update our items to the ones that we need to contain the indexed information, the index information, or the index attributes. In this case, we were interested in finding all the inventory items for a, what was it? All POs for an inventory item by date range. Okay, so that means that we would need to index all inventory items, hey, guess what, by date range. In this particular case, we're looking at probably a fairly relatively manageable data set, but let's assume that this is actually a really, really large retail organization that does aggregate on thousands and thousands of items. There would be some, we would want to know some information about how fast things are written, how much data we're reading, and how big are these items, right? To be able to define, how many items we can load into a single partition and retrieve in a reasonable time frame. But let's say again we're dealing with thousands. At some point we're going to spread this data horizontally across multiple partitions, and so as we start to create more and more purchase orders that are referencing the same inventory item, as we're aggregating this information on the GSI, I'm probably going to want to aggregate this thing by inventory items across some range of partitions, right? Let's say 0 to n partitions, It's probably only going to be maybe one for your average application, because again, it's just not doing that much volume. But let's say high volume, it'd be maybe 2 or 3. We're not talking about hundreds here, but we're spreading the data out. And as the data comes into the system and I start creating these purchase orders, every time I create one of these inventory PO detail items that references an inventory item, I would just say randomly between 0 and n, tack that onto my partition key. So I've created an inventory item partition that contains 0 to n, partitions on the partition key, and then on the sort key it would be our date range. Okay, so I would say what is today? Today is 7/7, I think. And let's just say it happened at midnight or noon. Okay, and so this is the only inventory item we have. So this will be like the only inventory. This is the only thing that'll show up on our GSI. If we go to our aggregate view here, I can see I now have one item, right, that shows up. It's and let me see. Oops, I screwed up the model here. We actually need to change this a little bit. If you notice, what I did is, if we're saying that I want to get all the items, what was it? Our use case was get all POs for an inventory item by date range, but I said, hey, get me all POs by date range is what I just did here. What I need to do is, this doesn't need to be an inventory item, it needs to be inventory ID. Now, I'm a lot less likely on the inventory ID dimension to be able to have to push into multiple partitions, but let's assume it's a really popular item. It's Prime Day in Amazon. This is really more of this workflow, and I've got a really large number of items that are being procured or ordered at a high velocity. Then I might need to spread it out. And now if I save this and I go back to my aggregate view and I look at my GSI, when I query by inventory ID on the partition key across some number of partitions, I get a date ranged set of purchase orders back. And so I could issue 2 or 3 parallel queries for inventory ID X with date range condition Y, and say, oh, look at my sort key. I used an apostrophe instead of a number. Oops. Yeah, I'm gonna have to change everything. Oh boy. That's what happens when you mess up your model. See, so let's go ahead and see what I just did here. Do I need to update my data? No, I'm just gonna keep that partition key. Okay, so we won't change anything here. Pretend that apostrophe is a 1. So now we're in, look at partition key, and I query at my GSI. If I query with inventory ID across a number of partitions, and I go to and give it a date range condition for the sort key condition, I will get a list of purchase order IDs. Really what I'm getting is PO detail items from these purchase orders, but it gives me the reference or the pointer back to the purchase order IDs, which I can then go back to and say, well, depending on the workflow, I could go back to and say, okay, get me all these, by purchase order ID from the table, just do a batch get item, or I could say, what is the data I really need when I select for this, and denormalize that data into the detail items, right? So oftentimes when you look at these workflows, I don't need the entire purchase order item. I only need some subset of it. In which case I would say, let's project that data down here if that's what I need, or maybe all I need is the list of purchase order IDs. Oftentimes that's really what we're looking for. So let's take a quick look at our next access pattern. Would be get POs by activity code for a given date range, and so it's a similar issue here. The activity code, if we look at our data model. Okay, the activity code is actually tied to the purchase order note. So what we're really doing is saying what activities were performed against, what purchase orders had this activity performed against them. And so what we're going to do is index the purchase order notes. And that actually that's good for us, because that means I can actually reuse the same GSI. And so this is what we'll call GSI overloading. In order to do this, I just need to add those dimensions to the PK1 and the SK, exclamation point. We can go ahead and add to our note items, right? So let's do that. Let's say edit data. And now I've got my notes, and I can say note ID, or I can say activity ID. And again, we'll assume that this could be relatively broad, large number of POs, high velocity of POs, and notes on POs. This is, going to maybe potentially spread out across some number of partitions. For 95%, 99% of your applications, this will not be the case, right? I mean, for most of what we just went through, when I looked at those, average retail data, transactions, things like this, you look at the purchase order flow for most businesses, for most, this will not be the case, that you will not need to do this. For Amazon, you probably would, right? And I know you would. So if I want to aggregate, let's say, orders by source, or orders in a given state across all Amazon services, retail services, then there's certainly going to be the need to spread things out. And this is what we're doing now. And so now what I can do is I can go ahead and save this information. If I go back and look at my GSI, I have two partitions. I have the inventory partition, I have the activity partition. Right, so I could query on the activity ID. Save this, and this gives me the ability now to query that GSI on two dimensions, right? By inventory ID, by activity ID. Both of those give me back a list of purchase order IDs. I can choose, again, maybe when I'm querying by a certain activity, I want to know what was the state of a PO, or what was the type of a PO, what was the source of a PO, and this could be the reason why I'm looking up POs by activity ID. I would then go ahead and annotate that information onto the note, so that I wouldn't necessarily have to round trip back and go do batch get items against a purchase order ID. Again, maybe I'm just looking for a list of pointers to those purchase orders. This is structured, delivers that out of the box, right? No projections and no denormalization. So let's take a look at what are some of our other access patterns now. We want to get POs by vendor, again, for date range. So POs by vendor, we don't really have a vendor note in our model, but we do have our top level, vendor relationship. Oops, you guys have been looking at you're not seeing the workbench. Here's the workbench, and I just described this, GSI1 that has two partitions that we can see, and now we can look at the query by inventory ID, query by activity ID. Apologies for that. I left you on the schema view for a little bit too long there. And when we have the data, what I did was, again, I've annotated the inventory items with a PK and an SK for the GSI. I've annotated the note items with a PK and an SK for the GSI. And that enables me now to query the GSI with two different access patterns, right? Inventory ID and activity ID. Right, two different query conditions, which will deliver two different types of objects, but they both point back to the purchase order that they're attached to, and that's really what I'm doing when I go for this access pattern. I say, give me all the POs for a given inventory item by a given date range. Give me all the POs for a given activity code for a given date range. We want to get all the POs for a given vendor, and so now what we can do is we can say, let's go back to our objects. And let's just say that we can annotate the POs by vendor ID and date range. So now when I look at my GSI, I've got three dimensions that I can query across: vendor, inventory ID, activity ID. I'm probably going to be spread inventory ID more likely to have to spread out across multiple partitions than the vendor ID, because this is probably not as dense an aggregation, right? And this is where you start to talk about the workload, right? How many inventory items per second are being ordered in your system? How many activities per second are being performed in your system? Again, if you think about the average purchase order system, not many. So you probably don't even need to do anything here as far as sharding goes. When you look at Amazon, a lot, right? So we probably do need to do something about sharding, right? So let's think about when you need to apply these things. Don't just apply them automatically. But I can guarantee you that, you know, by vendor ID in most systems, in 99.9% of systems, vendors aren't generating thousands of orders per second. So you're not going to need to necessarily worry about, you know, these aggregations on the GSI if I'm aggregating POs by vendor. And so usually a single partition by vendor ID would be, you know, more than sufficient. We want to get POs by associate by date range. And so this is where, if we look at the actual model, right, the relationship between the associate and the purchase order is really a many-to-many, and it's happening through notes. And so that's, again, we're going to have to kind of index to find the associates, you know, all the POs for a given associate, you know, by date range. I'm indirectly going to have to look at all the associates' notes, really, is what it comes down to. So we would really, that's what we would do. We would overload, or we would load additional attributes onto the note item to be able to, you know, create a second index is really what we need to do. So let's go back. We're going to go ahead and add another index to the table. Add some more attributes. This will be PK2. And we already have this SK exclamation point field, which contains the date condition that we need for the note. So we don't necessarily need to define an additional you know, attribute for this index. And so I wouldn't necessarily do that until we actually need to. But so let's go ahead and just add a global secondary index. This would be GSIA2. And it would be partitioned on PK2. And it would be sorted on our existing date sort key, and we could save that to our model. And now if I go and look at our data, I have an extra attribute here, and the only one that needs that is the note item. And so when I save that, now if I go back to my aggregate view and I look at notes, I'm showing purchase orders by associate ID by date range. Right, so that was kind of a neat little trick there, right? We basically just defined a new GSI, we added a couple attributes to an existing item, I get a new view on a new dimension and a new aggregation, and that's exactly what we're trying to kind of do here when we look at our model, right? So our first base table supports the get by purchase order, get by associate ID, get by vendor, and all the entity IDs. Our GSI 1 supports get by POs by vendor ID, by date range, by inventory ID, by date range, by activity, associates by activity, by date range. GSI 2 gives me POs by associate by date range. Some of these might end up being duplicates because an associate might have multiple activities on the same PO, but that's okay. Client-side filtering, you know, whatever. You can even add, you know, some sort of a filter by activity ID if that's potentially something you're looking for. And maybe let's take a look at how we can actually do this a little bit more selectively. Maybe what I'm looking for is POs by activity by associate, or by associate and activity. So let's take a look at how we might do that by taking potentially the activity ID for a given associate and moving it into the partition key. I'm sorry. Well, let's see. How can I do this? Well, what I wanted to do, if I created a second attribute here, this could be interesting. So let's go ahead and do that. Let's, if I created another attribute to index on for our GSI, instead of reusing that date attribute that we're already using, then I could actually create a faceted sort, right, which is another pattern that we use commonly in DynamoDB. So let's alter that pattern a little bit. Instead of saying I just want to get the POs for a given associate, what I really want to get is POs by associate and activity ID. And so I'd say let's alter our tables slightly and create a new attribute for GSI2 that's going to contain slightly different date information. And this guy is going to use SK2. We'll go ahead and save those edits. Now we can go back to the visualization. And so SK2 is going to have activity ID and date as the sort key. And if I save that and I go back and I look at GSI2 now, So I can query by associate ID, and I can say, hey, give me everything for activity ID hash date 1 and activity ID between activity ID hash date 1 and date 2, and activity ID hash date 2. That's a date range condition that works on a string sort, which gives me if I had multiple types of activities that an associate was performing against a PO, but I want to see everyone who did this particular activity and what did they do over the last 30 days in that particular activity across all POs. This would be another way to sort and search. But again, I couldn't reuse that date field we already had because I'm creating a new key. And that field contains a straight date, right? So let's take a look at our next pattern, which would be get incomplete PO items by date range. Okay, so this would be a second dimension that we are indexing our items on, and that would be a status, right? Incomplete, which would be basically not delivered, not shipped. This would be and we would again we would have now for these, since we've already created this SK2, we would actually need to duplicate the date of the particular item, of the particular order of the item, whatnot. This might be and this is because in this particular case down here on the notes I needed to get two different date range conditions. I couldn't use a straight date, I had to use activity date. So now if I want to index the inventory items on GSI2, I need to basically duplicate the date across the two sort keys. Not a terrible deal, but that's a small duplication of data. And again, we could choose to send these across some number of partitions if the velocity of the items that are being created is very high, or we could choose to, depending on the nature of the system, to ignore that. It all depends on the velocity of the workload, but I'm calling this out as a dimension where I would, in a design review, want to know, what's the velocity here? What's the transaction rate? What's the throughput of the system expected to be? And that tells us whether or not we actually need to start splitting the data out. And that's where you'll usually see that is on the indexes, because I'm indexing a large number of items on the table. The items on the table are generally speaking spread out and well distributed. Where we almost always see key pressure in NoSQL databases is on the indexes, because we're trying to aggregate large numbers of items into these things, and that's creating a lot of write pressure on the structures that are maintaining those indexes. So that's where we'll call that out, but it's not necessarily something we necessarily need to worry about depending on the system. But now again, we have overloaded GSI2 to be able to query on incomplete inventory items and get me all those POs by date range, potentially across some number of sharded partitions if the velocity of the workload is high enough. Okay. Let's take a look at our next pattern. Get POs by inventory category. Okay, so POs by inventory category means that I'm going to have to look at indexing my PO items, let's see, on another dimension. And so again, we can reuse, lucky for us, we can reuse GSI2. And so this demonstrates one of the more common things I like to do is reuse existing containers for new access patterns, because it just drives a lot of efficiency in the system. If I have all these patterns running against a GSI, then it's highly likely that the GSI's capacity utilization is going to be higher than if I have multiple GSIs, one for each pattern, because your application doesn't fire all of its patterns at the same time, right? So GSI overloading, table overloading, single table design is usually a way to drive a lot of efficiency in the system. And so this was get us, what was it? POs by inventory category. So inventory category is on the item, not on the PO. So this actually would mean we would need a new GSI, because my purchase order inventory items are already indexed on 2 dimensions. So let's go back and add GSI3. And to do that, we're going to add a few more attributes. And these were, let's see, that top level pattern was saying just POs by inventory category. So there's really no date range. It's just saying give me all the PO. Well, there probably would be a date range to that order. So let's say that they're to that access pattern. So let's go ahead and reuse our date, attribute we already have, and define a new GSI. And that's going to be on PK3. And we're going to add the sort key, which will be our existing date range sort, or date range sort key, which we have already on the item. And we can save those edits, visualize the model. And so now I have another attribute out here, PK3. PK3 is going to be on inventory category. So this would be, when I add the PO detail, I would add the category ID. And I would probably want the inventory metadata, the inventory item metadata when I do that. So let's go ahead, and this would be the first indexed attribute of a actual entity item on the table other than PO items. And so we're going to add category ID here. And for date, right, which is our date condition, we're just going to use the A record, which is what this item is. It's the A record. And the reason why we're going to do this is because when we look at the aggregate view, and now I look at GSI3, let's say that my query is actually saying, hey, get me all the POs by category item, by category ID in the last 30 days. If I query that particular query, I'm going to get all of the items, date ranged items that meet that condition, as well as this item, because it will always meet that condition. A is greater than the last 30 days in a string sort condition. So what's interesting here is to say I don't have to make 2 round trips to get the inventory item metadata and all the POs and the PO details for that item in the last 30 days, last 6 months, whatever your query might be, right? So it's just a little efficiency gain here as I avoid multiple round trips potentially. I don't know if that's really valid in this particular workflow in this particular app, but there's plenty of apps where it is, right? Where I'm looking at, get me all the events in the last 30 days for this entity. And you also want the entity's metadata, and I don't want to denormalize it. Well, that's a great pattern to use, right? Index the entity on the same index using a sort key, which is greater than any date condition, and then using a date range condition of greater than X, and you'll always bring back the metadata as the last item. So that's a little trick that we use quite frequently to reduce the number of round trips to the database, reduce the RCU consumption. Again, to go get this item individually, that's 1 RCU. So if I'm getting all the date range category by category ID in one query, and then I go back and do a get item to get by inventory ID off the table, I'm paying, and I'm doing that at high velocity, I might be burning a lot of RCU on the table, and this is not necessarily a really big item, so you'd probably want to get it in the first request instead of getting it in its own individual request. Okay, so get low inventory items. We're going to get down into indexing some of our other entities here, and we're getting down to the bottom of our access pattern conditions. So these would basically have some sort of inventory state. We can choose which index to put these on. I've got inventory items. They're going to have some inventory volume or whatnot, and I'm looking to get all, and if you notice, get all low inventory items. So maybe what happens is, individual inventory items have a quantity, and when their quantity hits a certain point, then they get marked as low. I don't necessarily want all these items to exist on the table all the time. I only want the items that exist, I don't want all these items to exist on the index all the time. I only want them to exist there when they actually are low. So the way to do that is easy enough. In PK1, we already have an attribute here called the A attribute, which describes the inventory item. We can go ahead and say, let's put this on GSI1, and we're going to put it in the low category. Now I'm going to hopefully not a high velocity or high volume of items in my inventory will be low, and the rate of change of this is not going to be fairly is high velocity. So we don't necessarily have to worry about spreading it out across multiple partitions. We can go ahead and look at this and say, now let's look at GSI1, and I can query the low partition, and it'll give me all my low inventory items. And this could be like a reorder workflow, maybe on every other day or every day at midnight. I run to say, get me all my low inventory items so I can reorder them. So I'm actually interested in getting every single item that's low inventory. and I can run a process that says either reorder or check order status or something like that. So I don't need a sort key condition here, but the index has one, so that's okay. Each one of these order detail items just gets annotated with, or inventory items gets annotated with that particular attribute. When an order gets processed, the quantity gets reduced, and maybe a Lambda function catches that and says, oh, but the quantity is lower than, its current, than it's supposed to be. I will then annotate low. As you reorder and restock, then what happens, I'll come in and I'll change this PK1 to be nothing. I'll just remove the attribute from the item. That removes it from the GSI. Now it doesn't exist there anymore. I don't have to pay for that storage. I only have to pay for these items when they're actually in that low condition, right? Once I remove that, it just deletes the item. All right, so let's go back and look at another access pattern here. Get vendor by vendor ID, we've got that. Get associate by associate ID, gets associates by activity code and date range. Okay, so I think we did that. We actually did that one already. I said, let me go get the, yes, I actually did. If we look at GSI 3 or GSI 2, and I query it, oh no, I want associates by activity code and date range. So we didn't actually do that. This was getting me all the activities, all the items that an associate performed by activity code and date range. But what I want in this access pattern is say, get me all the associates who performed a given activity in the last 30 days. Okay. So again, if we go back and look at our schema here, that relationship is defined through the notes table, right? What activities the associate performed on what POs. And so what we're really going to look at is creating another index on notes is what we have to do. And so notes appears to be, I think, our most indexed item on the table at this point. Let's take a look at that. And if we look at the note is already exists on GSI 1, 2, and no, it does not exist on GSI 3. Hey, lucky for us. So we can go ahead and say this needs to be GSI 3 is activity code and date range, which is actually, that's perfect because it's already defined as a date range condition, a pure date range condition. Notes define the activity. So all I really need to do here to get all my associates by activity code is put the activity ID in PK3, and that drops those items onto my GSI 3, which now means I can query by activity ID and date range, and it brings back a list of all of the, not only the purchase orders, but the individual associates that executed that activity on those purchase orders. Right, so that's the final access pattern we had, and that kind of drops our whole model into perspective here. If we look at the aggregate view of the data, we've got all our select by ID. If we look at the GSI, we have, select on various dimensions by date range, select on inventory status for inventory items. We have GSI2, which gives us all of our incomplete PO items or PO details, which tells us which inventory items haven't yet been processed for given POs. We can get all of our associates by activity ID and date range. If we look at GSI 3, query on category ID brings back all of my inventory items as well as the inventory metadata. If I query on activity ID, brings back all of my associates who performed that activity and the POs they performed them on in a given date range. And so we've kind of blown through all those access patterns and demonstrated how to create that model in this particular exercise. So this is the primary value of the NoSQL Workbench. It's to be able to sit here and tweak on things and play with the models and be able to satisfy your existing access pattern or your defined access patterns and see what does it look like. But one of the really cool things about the tool is now that I've done this, I can actually go in and I can commit this data into DynamoDB, right? So I've got a connection that's already defined. I can take this table and I can wait a second. I can build operations against the table. I can actually create this table I can actually commit this table to DynamoDB and create a real table that I can actually go look at in my console, and I can actually write the data into it. I can query data in and out of it, and I can see what those query result sets are going to look like once this table's been created. So let's go ahead and see what happens now that I've gone ahead and committed that data. Right, we can see that that operation executed. I should be able to go to my DynamoDB console here and actually see that new table and the where is it? Did it create it? I got interrupted by my chime. I didn't actually see if the operation completed. My default connection is, am I looking at Oregon? Where's my table? I wonder if it created in a different region than I'm expecting. Save connection field is required. There it is. Yep. Commit. Table creation failed. It already exists. Okay, so I need to look at my. Hold on 1 second. I bet you my default connection that got changed. I need to take a quick look. No, it says US West 2, so this is odd. This is really strange. I don't know why this is happening. It says it exists. I bet you if I go in, I don't know why it's not showing in my console though. That is just so strange. I don't know if I'm using the right account. That might be my problem. I bet you that is exactly my problem. So let's go. I bet you that is my problem. I'm sorry. I'm displaying a different account ID in my console than I have configured in my default credentials. In my that's the only explanation. But what I can do is I can go ahead and look at that table. I can open that connection, and I can see yes, this is actually defaulted to the U.S. East region. That's probably where my table is. Let's go ahead and look at that. Yeah, there's our data. There's our table. I knew it happened. It happened someplace. And we can see this is the data it actually created. It took my sample data and it loaded it into the table. And now what I can do is I actually can go in there and look at the table itself, and I can query the data on that table, and I can see, you know, what that thing actually might look like when I build those queries. You know, and let's go ahead and I can actually build operations. I can say, let's say, what does a query look like? You know, partition key is, let's say the partition key equals purchase order ID. There's no projection expression. There's no filter expressions. Let's go ahead and, partition key equals purchase order. That's what I want to see. And I can execute that query and see it'll bring back the subset of items from the table that match the query conditions. So when I go ahead and build my table of access patterns and I add the query conditions that I think should work, I can actually validate all of that here in this tool. You know, if I scan the table, it brings back everything that I inserted. If I execute these specific queries, that will, and I can actually build these operations and generate the code, right? So not only can I, you know, go ahead and create that, you know, here it's validate it, execute it. Now I can go ahead and generate the code for it, and this is code that I can copy and paste into my project. It offers Python, JavaScript, Java. So again, really valuable tool that you can use to help, you know, just accelerate your development in DynamoDB, because not only can we model the data in this tool, but we can deploy the sample data into a real table, validate those queries, all those query conditions. We can look at the result sets in the tool, and then when we know things in the conditions match what we expect and the results match what we expect based on our query conditions, we can go ahead and generate the actual code that we're going to use in our applications and cut and paste that code, generate an executable binary that we can validate from the systems that it's going to intend to run on. It really is a valuable tool for you to use in all aspects of your product development lifecycle, right? And especially your design and coding of your applications. It's invaluable in modeling, but it also helps out when you get into the actual implementation and execution as well. So that's what I've got for you in this session today. If you guys have any questions, feel free to fire up online. I apologize for the hiccups here. Again, this was a completely blind exercise. I didn't even look at that schema since the time I selected it and posted it online on Twitter last week, and we just modeled it in real time today. That was less than an hour with all of the other dialogue I give you. So it gives you an example of it's not hard. It's just a matter of familiarity, and you too can also get familiar with these tools. It's not necessarily something that is rocket science. I mean, I've been doing this for a long time, but honestly, these patterns that we are explaining to you today, these are things that we just developed in the last couple of years, and we had to develop quickly, and we did, and the knowledge is spreading now across the entire development team and the entire NoSQL community. So it's just like relational databases. In the beginning, you didn't necessarily know how to use it. Somebody had to teach you. So take this opportunity to poke around, play around, and again, don't ignore what you can do in the free tier. Again, it's amazing with DynamoDB. These are always free. 25 gigabytes of data, 25 WCUs, 25 RCUs. There's no expiration on that. And as a developer, you can launch a completely new application service and have access to serverless technologies like Lambda that also have free tier, and even EC2, which is more limited, but you've got all kinds of options to be able to deploy new application services for absolutely $0, which is unheard of, right? So, and these things can perform some real work, right? And you look at 25 WCUs, especially with burst bucket and burst capacity on the table, you can do some real serious workloads, 65 million requests not a second, but a month, easy. On these types of free tier workloads. So definitely something to think about. And again, I appreciate all you guys taking your time today to come listen to this. This is really cool. We just started doing this. If you like it, then we'll keep doing it. And I appreciate the response so far. So thank you so much for taking the time out of your day. And that's what I got for you. So again, any questions you want to throw up for me? I think the moderators have been online, so hopefully they've been able to take care of most of those questions. And hopefully I'll see you next week. All right. All right. Thanks a lot, guys. Appreciate it. Talk to you later.